Swayam Prabha. Digital India. Educated India.
We will be talking about applications of geosynthetics in unpaved roads in this lecture, and essentially this when the soil is poor, we try to if you want to design the road, you have you do the CBR test, which is nothing but a strength test, and we try to see that the thickness of the pavement is arrived at based on the CBR value. But in some cases there are many other issues that like still there could be many other problems associated with rideability and comfort and many other issues like performance. It is very important that some of these aspects are considered in the road design. What we will address today in this lecture would be that we will study the why these geosynthetic materials are required in roads. Actually, there are two types of roads. One is called two types. One is unpaved road and paved road. Essentially, unpaved road means just there is no treatment to that, and then the soil is very poor, but you try to make up by making some sort of crust over it, and then we make like some thickness that you get based on CBR value. We know the in situ value of the in situ CBR value, and then you try to put some sort of cushion because the CBR is so low. Then we try to add some more like a granular subbase layer, GSB we call it. We normally have the subgrade and then the subbase and base course, and after that we have a wearing course. So all this below this wearing course, it is called unpaved section. Okay. So we will see what is the use of these geosynthetics in pavements, their performance benefits, and these conditions under which the geosynthetics are very useful. How do you design these pavements, and we will have an example here, and what about the survivability criteria and some applications in paved roads. As I just mentioned, this is like a typical road section, which you see that it is very difficult to do that. So you have the soil subgrade is so poor, but then based on the CBR value, you can come up with some sort of thickness, and then you can make it unpaved road. Okay. After this, again you have a pavement layer constructed on that. People have seen that the geosynthetics help in significant savings, improved performance and good serviceability both in short term and long term. These are very important, like savings is one thing, then improved performance. I was talking about rideability and comfort, smoothness on the roads. This is very important, and long term performance like serviceability is also very good. So all these three things are very important in pavement design using geosynthetics, and this is where they are very useful. And other thing is that even in some conditions, very difficult conditions like marshy stretches, like very soft soils, organic deposits and unexplained soils, one can construct. That is a very good advantage, that it is very difficult to handle them, but at the same time if you have these materials, one can construct good roads. How do they help? So the functions of the geosynthetics in roads are that, like, it acts as a separator. As I just mentioned, you have two dissimilar materials like subgrade and aggregates. You try to see that they do not get intermixed. So geotextures and geogrids perform this function by preventing penetration of the aggregate into subgrade. It is called localized bearing failures. In fact, what happens, there are two dissimilar materials. The bearing capacity of what you call the subgrade is, we have some bearing capacity, and if you put it in if you put a granular subbase, the bearing capacity increases. GSB or the granular subbase has a better bearing capacity because it is a more frictional material. Like, so when you have that, but then over a period of time, because of the repeated action of traffic, repeated action of loads of because of the traffic movement, the subgrade material goes up and that aggregate material comes in, and then there is mixing of both materials. It like bad plus good becomes bad, it's like that. So, essentially that's a very not a correct thing, and if you have a separator between them, each will perform their functions in a very satisfactory manner, with which you must have designed based on those lines, like you must have taken a CBR value subgrade and you get a thickness. So, we do not assume that there is a mixing up, right. So, that will not happen now. The second thing would be that soft subgrade soils are very susceptible to disturbance during construction activities such as clearing, grubbing and initial aggregate placement. Geosynthetics help in minimize subgrade disturbance and prevent loss of aggregate during construction. In fact, during construction they are quite effective, like in some places like soft soils, it is very difficult to clear them, clearing and initial aggregate placement, like as I just mentioned in the case of other examples, like if you try to put aggregate, it gets mixed up, and you may lose some 30% of the aggregate just to see that you have some hard material in the beginning. So, but if you have a geotextile, exactly the quantities of aggregate you have placed. That way the contractor would not claim that there is a loss of aggregate for me, sir, and there is no problem here. So, that they help in that prevention of loss of aggregate. So, this is what I just mentioned, like you just have a soft subgrade, you have geotextile, and they behave in this way rather than this way, right, where there is a mixing up is here, right. So, the other advantage that we have is that you have a geotextile, it is nice, but it is a separator function right now, but it helps as a it has functions of filtration as well drainage and reinforcement, all of them will help. So, geotextile acts as a filter to prevent fine particles from migrating into the aggregate layer, due to high pore pressures induced by dynamic loading. Then it also acts as a drainage, you are trying to put it to the side drains also, you can take it and then put it to the drain layer nicely. So, pore pressures are dissipated, and also that you can provide some sort of drainage as well. So, these two, and say even reinforcement also helps, and the way that reinforcement helps, we will see that. Say for example, as I just mentioned, like confinement effect, we had talked about inward shear stresses and outward shear stresses concept in embankment and soft soils. Here also same thing, there is a lateral confinement of the base and subgrade through friction and interlock between the aggregate, soil and geosynthetics. Because of the interaction between the geogrid and aggregate and soil, there is some inward lateral restrainment or the inward stresses, because of which there is some confinement effect inside in the opposite direction. The load is applied, but the force is in the opposite direction, and so it performs better than a conventional conventional pavement system. So, the other one is the increase in bearing capacity by forcing the potential bearing capacity failure mechanisms to go along alternate higher strength surfaces. The third one is the membrane support of the wheel loads. I will give you the example, like this is a wheel load, it is acting, and then there is a pressure like this, and because of this there is you have placed a geogrid here, and there is a lateral restrainment on both sides. This is what we call confining effect. The second thing is that we assume some sort of failure mechanisms like this, bearing capacity failure mechanisms, and if you put a reinforcement here, there is a possibility that this failure surface gets altered, it is a new failure surface which can be different, and the shear resistance along the failure surface can be much higher, because it gets deflected away from the original one, and so if we just take the length of the failure surface will be bigger, and along the length of the failure surface the shear resistance is also more. So, we take that assumption and then calculate the load bearing capacity of the subgrade here. The other one is, so this is called bearing capacity increase. The first one is lateral restraint, the second one is bearing capacity increase, the third one is membrane tension effect. Particularly in soft soils, and if there is no friction between the soil and reinforcement, what happens, like there is a when there is a force load applied, it gets like it's a tension membrane gets deformed, and the force in the membrane acts like this, that the vertical component of the vertical support component of the membrane resists the load in the load from the top, like the membrane tension in the geosynthetic, it acts like this, and so there is some resistance here, though we do not assume that there is a so much of interaction, just because of the membrane, like a balloon, right. So, this is actually also valid in the case of a very soft soils and all that, where the friction is quite less. So, all these three mechanisms can be very useful to calculate what should be the effect of reinforcement, right. So, how do you understand these benefits? Like say for example, this is separation function, filtration function, reinforcement. Reducing the intensity of the stress on the subgrade, the separator function helps. Preventing the subgrade fines from pumping, both separation and filtration helps. Preventing contamination of base materials, filtration helps. Reducing the depth of excavation, yes, separation helps, and reinforcement also helps. Reducing the thickness of the aggregate required for stabilization of subgrade, separation and reinforcement help. So, the mechanisms of use or the benefits, they are like this. So, these are very useful things, like so for example, you would like to reduce the thickness of the aggregate layers or whatever thickness of the crust or the pavement. These two will help us, like separation function, reinforcement function. These are all extra benefits that we have. So, this we can try to quantify here, because it is possible for good design procedures are possible. And other thing that we have is the disturbance of subgrade construction during construction is less, and that is in fact supported by separation as well as reinforcement function. Allowance for increase of strength over time, yes, filtration, because it enables the drainage effect, it is possible. Reducing the difference settlement, reinforcement function helps, because that is one important thing, in the transition areas from cut to fill, again it helps. All the three things help. Reducing maintenance and extending the life of the pavement, all of these materials help in some sense, and giving the benefit of the performance, right. So, this is okay. Now, what are the conditions under which the geosynthetic materials are useful? In fact, if it is a very poor soil, excellent, right. Like all the soil classification, like is based on the USCS classification, and like CL, CH, ML, all this, they are quite useful. PT soils also, and actually in ASTO code you have A5 to A6, they are all very poor varieties of soils. If you just say ASTO code, the lower numbers are for good soils, these are for poor soils, and if the undrained shear strength of the soil is less than 90 kPa, okay, and CBR is less than 3. Actually, I want to just give a simple correlation here, which is available in literature. 1 kPa is equal to 1% of CBR is equal to 30 kPa roughly, okay, and if the moment of the resilient modulus is what is another term that we have, it is less than, it is close to 30 MPa, it is also quite useful. And in high water table areas also they are helpful, because of the drainage and all that. Then high sensitivity is also, they are quite useful, where the sensitivity is quite high in soils, they are helpful. So, how they are effective, to what extent they are effective is a function of the subgrade soil strength. If the soil subgrade is like you can find out a vein shear test or a CU test, you will get the undrained shear strength, say 60 to 90 kPa. As I said, CBR will be in the range of 2 to 3, because 1% CBR equal to 30 kPa. So, at that time the functions like filtration and separation are very helpful, and if it is somewhat lesser weak, this is somewhat stronger in this group, and if the CBR is between 1 and 2, filtration, separation, possible reinforcement action may help. But if the soil CBR is less than 1%, all mechanisms of improvement are very useful. like you can design a pavement based on IRC guidelines or whatever. One can design, depending on 1% CBR, what is the thickness of the crust required, one can calculate. We will show some calculations on these lines in this lecture today. So, how do you go about design? Design is that, like as I just mentioned, the reinforcement helps in the provision of a geotextile helps in 2 ways. It acts as a separator and it also acts as a reinforcement layer. So, first thing is that I do not want to consider the reinforcement effect. I will only make it I assume that it works as a separator, right. So, in that case we will have a design procedure that we will see, and it is quite useful. Then you will also you know about rut depth. Rut depth is nothing but a permanent deformation in the soil, like if there is a, like say for example, I want to give an example. If there is a vehicle continuously going, there will be a depression which is called permanent depression. It could be the maximum depth of rut could be about 50 mm to 100 mm in some cases. So, you can, when the rut depths are small or loads are quite less, like say a simple village road where there is not much traffic and it is fine, one can take a geotextile which can just work as a separator. Anything which can work as a separator, our objective is to see that they do not get mixed up, nothing else. So, you can use any material that can serve that function, but durable, right. So, that is one thing. So, that can be very useful for thin sections or where the traffic loads are less, and also the rut depths, rut depths are like quite less, okay. Like you want to rehabilitate a road, say for example, which has lot of vehicle tracks, and you must, if you go in a village, you see that along the track, along the road, there will be some depressions, that is called rutting. So, that is one thing. The second thing is, if you put a somewhat stiffer material, like instead of I want a geograde which is somewhat stronger. So, I will be able to take advantage of that, and then I can use it for live loads which are higher, and rut depths are also higher. Like as I just mentioned, the rutting depth, the what is that, membrane effect. Membrane effect is there. Higher is a depression that you have, higher is a tensile force mobilized. So, if you want to really handle depths of ruts being higher, you need to have higher tensile force, and it may consider thicker roadways on soft grade and all that, right. So, there are some more studies that people have done, and people did lot of field studies as well on clays, and like if the traffic, we know that what is the standard load, it is 8 tons, in Indian standard code, it is 8 tons or 816. So, it is 8 tons we call it, okay, 80 kilonewton per meter, or 80 kilonewtons actually, it is not meter, actually 80 kilonewtons, and or it is also same as even in US code, the same thing is done. And without geotextile, and if the rut depth is less than 50 mm and the traffic intensity is more than 1000 mm, people have worked out bearing capacity. I hope you know that the bearing capacity of soft soil is 5.14 Cu, right. If you know the Qu equal to 5.14 Cu. So, that is the ultimate bearing capacity of the soft soil. So, what does it mean? 5.14 means its ultimate strength has reached, right. So, if anything less than that, actually that what is that 5.14 is nothing but the bearing capacity factor. So, without geotextile, if the rut depths are in this range of less than 50 mm, people have seen that the bearing capacity factor could be in the range of 2.8, one can work back, okay. And geotextile, its rut depths is more and traffic is less, it is 3.3. There are some empirical or some reports that people have presented, and with geotextile less than 50, the same number 1000, its bearing capacity is the factor is 5, and then if the rut depth is there, it is little increase. Actually, this gives an interesting observation that roughly the bearing capacity with and without geotextile, there is an increase, right. Say for example, you take only a red depth of 50 mm, less than 50 mm, the bearing capacity increases from 2.8 factor 2.8 to 5 it increases, from 3.3 to 6 it increases. This is a very important observation, and that is useful in the actual approach, theoretical approach that we have. In fact, Giroud and Noire approach is one of the popular approaches that people have worked on earlier, and it is developed in 1978 in an ASC paper, and of course, there are a lot of modifications, but for the case of simplicity, I am trying to illustrate this method by use of the design of this pavement by this method. Okay. Actually, you have a normal highway vehicles, it creates a bearing, you have certain load over which that traffic load acts. That is given by, say for example, B is the one dimension breadth in the breadth, it is nothing but the applied load P, P is nothing but the standard axle load divided by the tire pressure, right. So B is square root of P by Pt, and so L is nothing but 0.707 times B, and this is what is that, it is an impression or the area of area over which the load is acting. The second thing is that suppose you have a high construction equipment, definitely you have wide or double tires, B you can write in this form, B equal to square root of 1 point, it is a little bigger, P by Pt, and B L equal to 0.5 B. Okay. So, this is another way of approach that they have proposed, and the how is that load is acting here. Say suppose I put a reinforcement, how does it work? Actually, what I am doing is that, see, there is a, you apply a standard axle load here, this is a B is the dimensions, and the L is in the opposite, the perpendicular to that, and we assume some dispersion angle, right. This is the standard, in say for example, stress distribution we assume, and we assume that when you apply a you consider the load displacement curve, like this is settlement, this is applied pressure, and you know that I told you that it increases to 5.14 cu, right. Pi plus 2 into Cu is the ultimate bearing capacity of a soft soil. Why you are talking soft soil? Soft soil is poor, actually, that is the reason CBR is slow. So, this comes to 5.14 Cu is a fully plastic region. Okay. Then this is, we just come out to a region where its soil is elastic, and we do not go beyond that, and we assume that though there is a non-linearity here, we assume that the soil is linear up to this point, up to a point pi Cu. Okay. So, the elastic limit of the soil is given by pi Cu, the plastic limit of the soil is given by pi plus 2 Cu. Okay. So, this is all the elastic region, this is the plastic region, because the deformation starts accelerating from here. So, how do you go about this? Say for example, we know the tire pressure and all that, and how do you take the load? In fact, P is nothing, like we have seen in the previous diagram, you have applied a load P, and what is the load that is coming here is what you should calculate. So, in fact, if you take the load dispersion angle, this becomes B plus 2 H tan alpha, where alpha is the angle of dispersion, right. This is H tan alpha and this is H tan alpha, so twice, so B plus 2 H tan alpha you will get. So, whatever is the load that comes here gets reduced, because it is now over a wider area, right, and if that so we'll see this, how this becomes converted to what we need. So, P is nothing but P divided by 2 into B plus 2 H tan alpha into L H tan alpha, this is the terms. Okay. So, the total pressure gets divided P by 2 into, this is what you get. So, as the analysis is not very sensitive to the exact value of tan alpha, and experiment indicated the alpha lies between 0.5 and 0.7, alpha may be taken as 0.6. The dispersion angle that we have in the angle alpha is not very sensitive to this, and then we can take it as 0.5 to 0.7, average is 0.6. So, if you do that and use that, you will get into B into 2 is B plus 1.2 H in this expression you will get, right. So, as I just mentioned, the bearing capacity is elastic bearing capacity is pi Cu, which is QE I call it, okay. Then QP is pi plus 2 Cu, where Cu is the underlying shear strength of the clay. Now, what I do is that I do not want any mixing of the aggregate and clay, and if I maintain the loads within elastic range, the possibility is that the soil is also elastic and aggregate is also elastic. So, there will not be much mixing. So, they come back to their original deformations and I do not have any problem of mixing. But, so what I do is that I will try to calculate that load, it is suggested that in the absence of geotextile I am not putting the load. So, I would like to limit the load to just Q based on elastic limit. So, pi Cu is nothing but that value, and I just mentioned P divided by, so this is the load right now with geotextile, it is a load at which it is acting, this load now is coming on the subgrade, right. Pi Cu is equated to this. That is one thing, like for example, that equation whatever I have given just now helps you to calculate if you know the underlying shear strength, say for example 10 kPa if I say or 5 kPa I say, and load I know P axial load, I can get H value, right. It is a very nice example on how to get how much of thickness I have to provide. Only thing is that I have not provided the traffic load repetitions. So, how do you do that? That whatever we have seen the previous expression is valid for light traffic and small repetitions of loads, but when the load the aggregate depth must be increased, because when the traffic load increases definitely you have to increase that. So, we call that as H naught. Now, the revised H naught becomes this expression, people have done lot of experiments and came out with this expression, which is in terms of the load number of loads repetitions n, okay, minus 294 in one R is called a rud depth, okay, rud depth in excess of 75 mm, okay, 7 point whatever rud depth in whatever the units, you have to put in the appropriate units here. Cu is in Newton per meter square, okay. So, if you know this number, then it also takes care of, say for example, this will be you may get some H in the previous value, but this H will be little higher because you are considering the traffic load as well, okay. That is one thing. So, we know how to calculate the thickness without thickness of the what is called the pavement without what you call much traffic. Like if the traffic is very limited, I know how to get the thickness of the pavement, but if the traffic is more and if I know the load repetitions and rutting depth, allowable rutting depth, I know the H naught. Now, the other one is that we are trying to put in terms of the standard load, standard axial load. Most of the time you have the vehicle axial the axial loads are different from standard, like instead of 8 tons it can be 12 tons, 16 tons, all that, right. So, what happens, because of the repeated nature of traffic, the possibility is that it undergoes high deformation than what you expect. So, one should really understand convert all the higher load effects into standard axial load, okay. So, how do you do that? You have an expression here, n is a standard axial load, by n dash is a non-standard axial load. Say for example, 12 ton, okay, standard axial is 8 tons. So, in this case P dash is 12 tons and P is 8 tons. So, if you just put those numbers and then the P dash is non-standard and N dash is non-standard. So, both these loads 12 tons and we know the repetitions, how many, you do a survey right from the evening, how many vehicles are there which are of non-standard quality, non-standard specifications like axial load essentially, and you can convert using this equation non-standard ones to standard ones. this is one type of equation that people have been following, and in fact IRC code also to some extent follows this, because this is based on the deformation criteria and all that. But some more advanced, some more research shows that a ratio of 6.2 is much more safer. That is one important point. So, this also helps in calculating the load repetitions of standard load, given that you know n dash and p dash. So, what is that we are working here is that the geotextile helps in confinement of the subgrade soil, greater spreading of the load, and like as I said, geotextile works in tension, right. Geotextile works in tension, and the confinement effect of the subgrade is very useful, that we have seen, and the openings in the some of the geotextiles and geogrids definitely provide this confinement effect. Okay, that is when we have seen that, we know how to take care of it, and assuming that geosynthetic deforms to a parabolic shape, like we have an assumption. See, the thing is that load that is there in the what is that, you know, because of the membrane effect is what I am trying to put here, that is given by Fg. You know, the thing is that load is acting like this, the tension in the geogrid acts in this direction, and how much of tension you have to calculate is in this form, load due to that uplift force is nothing but it is a function of, actually it is J E into 1 plus A divided by 2S square, it is the power minus half and A, where G is the tensile stiffness of the geosynthetic, E is a geosynthetic strain, actually it should epsilon or whatever, so it is okay. A is a factor which is 1 by 2 into B plus 2 H, B plus 1.2 H. S is the settlement of the beneath the tire. The Fg reduces the load P, and hence the corresponding relationship is given by, you know, what is happening, the load is reduced. This equation we just gave because of that previous like without this term is because of the tension, this is because of separation function. So, what we assume is that by we equate it to pi plus 2 Cu, okay. We assume that it is equal to pi plus 2 Cu, and what we are assuming is that I told you one simple assumption that the elastic limit, it's the load is pi Cu and it becomes pi plus 2 Cu at the plastic limit. Now, with the introduction of load, I will say that load can be taken from elastic to plastic only, because the contamination is not there now. So, what I say is that whatever is this total thing with the geotextile, now I have a Hg as a because of the geotextile, that is equal to P divided by the same thing, and I equate it to pi plus 2 Cu, instead of just in the previous time what I did was I just equated to pi Cu only, because then I assumed that there is no geosynthetic. Now, I have a geosynthetic material and I assume that contamination is not likely to occur, because the soil is not now they are all separated. So, I can safely take that the load that maximum it can be applied is pi plus 2 Cu. So, there Hg is the thickness of the membrane, thickness of the fill. So, how do you get the savings now? What is the savings in geogrid thing is that H naught is the thickness that you got considering traffic load repetitions and all that, that is H naught, and Hg is the due to geogrid, how much is that. So, H naught minus Hg will be giving the savings in the aggregate. Okay. I will show you this by means of an example that may be much clear. An unpaved road, like it is about 5 meters wide, is subjected to 1000 passes of a buckle or whatever, you can say 2 axle loads like some small vehicle, and each axle load is 120 kilonewtons. It is a little higher than 80 kilonewtons, which is standard, and each axle of the truck, there are 4 say you have an axle, there are 4.2 wide tires inflated at tire pressure of 700 kilonewton per meter square. The underlying soil has an underlying shear strength of 30 kPa and the aggregate is sharp. Okay, why these things are required is in terms of the serviceability specifications, this is required, and has a unit weight of 18 kilonewton per meter cube. If the acceptable rod depth is 150 mm, determine the road base with width using Gerodner approach. That is a question. Okay. So, what we are trying to do here is that, so n dash we know, n dash is 2000, and so we know that it is 80 by 120 is what you have to put, and as I said 3.93 can be used, but I am using a factor of 6.2 here to get the equivalent load repetitions. You can see that it is very significant. 120 2000 repetitions of 120 kilonewtons are equivalent to 24,000 or nearly 25,000 load repetitions of 80. It is very high because of this factor 6.2. Okay. So, you can see that the damaging effect of what is that higher axial loads. So, the loading is now equivalent to this 24705.6 passes of the standard axial load of 80 kilonewtons. Hence, I am using this term H naught is one thing that I said earlier, and use this term now here, like this term comes here, rod depth is also known and Cu is known. Oh, there is some error here. I will revise this equation. So, it comes to 0.8, okay, 0.8 meters if you just substitute all the terms, and for the construction plant and with wider double tires, you suppose I am using a construction plant, these are the equations that I just mentioned, and so you know what is the thickness of the road now. Say for example, in the previous class we have seen that it is using all those equations you get 0.8 thickness. Okay. Now, I should get what should be the thickness if I use geosynthetic, that is a question. As I just mentioned, I now equate it to elastic bearing capacity pi Cu. P is a standard load of 120, and I use B into B plus 1.2 H and all that I calculate, and I get, you solve for H equal to H naught 0.357 and you get 0.36. Now, you assume that ultimate bearing capacity is on these lines, and so again you get Hg here, you get 0.22. So, 0.36 minus 0.22 will be the change in the savings because of the aggregate. So, this is what it is, and now that is why it is because of the as I just mentioned, we are increasing the load from elastic to plastic because we assume that we provided a geotextile which cannot allow contamination. So, contamination is prevented by this geotextile, and because of which you can go for little higher loads can be higher, and so in the previous case is 0.36 and it is 0.22, the difference is so much. So, you also have this number 0.8 which is nothing but without any considering the load repetitions, considering the rod depth, you have this number 0.8. So, 0.8 minus 0.14 gives you the actual depth with geotextile. So, you can see that it is about a good savings is there in the with just separation function. Now, how do you consider the stiffness of the geosynthetic or the reinforcement function? Okay. We know that because of this tension membrane effect, the possibility is that the load gets reduced, and assume that the stiffness is about 100 kilonewton per meter and the strain is 10%, and the settlement is about this number, and the thickness with the geosynthetic reduces to 0.18. Okay. So, 18 centimeters. So, what I meant was that in this case previously it was I will just show you the previously, it is about 0.14, and now in the same thing you put that, the thing is this term has to be into that equation again. It reduces to about little extra, instead of 0.3 we have done, what we had done previously was 0.36 minus 0.22, right. You can just see in the previous step 0.36 minus 0.22 is what we did, and that leads to a reduction of the final thickness will be 0.66, and this 0.14 is a reduction because we did like this. Now, since the geotextile acts, you can the ultimate bearing capacity further increases, right. So, like because of this factor here, like the load is also taken care of by the tension force mobilized like this. This is a term, extra term that you get, and once you substitute all that, you will get a number which is little lesser, So, what it means is that it is a marginal difference is there. In fact, with the depth in the geosynthetics, it can be instead of earlier what we had was 0.66, now it is 0.61. So, if you consider the geosynthetic material stiffness on the reinforcement, there is a marginal difference, but the separation alone is good enough, particularly if you are trying to do a village road. You can just put a separator, nothing else. Separator is much cheaper, whereas the reinforcement is somewhat expensive. Consider that it is like maybe 3 units in without just as a separator, but it can be 4 or 5 or 6 units if you want a good reduction in settlements and all that. So, it is a good difference, is what one can say, that with just separation function alone one can achieve some significant differences. I would like to tell you one more thing, was that the calculation is a trial and error procedure. What we should do is that the same you have to put it here, the term, and then calculate which value of how this you have to do either by trial and error or solving. One can get this and get this Hg value. Okay. Or it is possible to do some trial and error procedures and then get this results. Now, as I just mentioned, survivability of the geotextile we just discussed, and selecting a geotextile for either permanent or temporary roads depends on the survivability criteria. The survivability criteria are not based on any systematic research, we should accept that, but it is just the properties of the geotextiles which have been which have performed satisfactorily as separators in temporary roads and similar applications. Like we have seen the case of filters and drainage functions, where a separate we had a separate heading, survivability criteria, and they had certain specifications, like it should be the grab strength should be this much, puncture strength should be this much, all that which are only the specifications are drawn in such a manner that you do not have a difficulty in installing the field and they do not get damaged in the field while doing things. That is it. So, if they are able to satisfy the requirements, it is fine, you can use it as a separator. So, so the geotextiles and their survivability, that is already given in some standard, the manufacturing literature, it is given. Like if you buy a geotextile of a particular grade, they will clearly give you that, yeah, this is the apparent opening size, this is the like if you want to take the permeability criteria also in pavement design, apparent opening size is required, and if it is just a reinforcement function is required, its stiffness is required, and then separation, if you are only talking about survivability criteria, only that what is that, handling stresses, like how much of load it can take, like if I just take this load and if a big stone falls on it, it should not get punctured. So, what is that puncture resistance? Is it how many newtons it is, or what is the force it can take without getting punctured, is what we like to see, and these are all by trial and error and then by practical applications and experience, and people have standardized these numbers for different applications. And if you are very particular, one can get the testing done field tests, lab tests, all that for the supplied products, and also in the field also one can do what could be the bearing strength, what could be the actual load and all that one can see. So, I will also would like to highlight some more applications. So, the unpaved road is that where you are able to decrease the thickness of the pavement to some extent by using the concept of separation, and also one can use reinforcement. And if you think that the road drainage is a problem, you can do a filter design. And then the most important thing is, once you do a paved road, what is next? You must make it paved, right? You have to have a wearing course. How do you do that? And do you think that geotextiles are useful here also? One should understand, yes, they are very helpful here also, because I will tell you that they can be used in many places here also, like the appropriate locations are that, like the thing is, you have a sub base, first is a subgrade, then sub base, base and wearing course. So, at the interface between a granular sub base and subgrade soil, right in the beginning, like where you have first is a subgrade, next to that put a geotextile and then take a sub base. The other thing is, below the wearing course also you can keep, beneath the surface overlay to a damaged pavement. So, I will discuss some of these things much more detail in a separate lecture on paved roads use. And what I want to say is that all these things are quite, in all these places they are quite effective. Okay. So, if I want to put at subgrade to sub base interface, placing this level, placing the geotextile at this level reduces the possibilities of rutting, and to some extent reduces the thickness of the sub base, besides controlling the contamination of sub base by fines from the subgrade soil. What we are doing is that, like what are the methods by which, or what are the failure modes of flexible pavement? One is rutting. Rutting means that formulation of thick, or whatever depressions you call it, that is called rutting. Then the fatigue. Okay, the fatigue and rutting are the two things. Fatigue is because of the load repetitions, number of load repetitions that you have, and fatigue and rutting are two main criteria, at least in if you look at pavement design for flexible pavements, right? Bituminous pavements, both are quite usual, right? So, if you are able to place that geotextile, I know the thing is that rutting occurs at the topmost portion, bottommost portion of the, it starts in the subgrade actually, you have a all that sub base and all that, and close to that, if it bends like this, the tensile strains are there, then it is likely that it leads to rutting, right. So, but then if you are able to place that little above, the advantage of putting that in a wearing course helps in restriction of reflection cracking, reduce rutting as well, because it takes care of some load on the from the instead of transferring it somewhere down, it just takes care of some load at the top layers itself. Restriction of fatigue cracking, because of the alternate or repeated action of loads, the fatigue cracks do develop, and in the areas such as high contact stresses, or where you have heavily trafficked areas or taxiways, where in runways and all airfield pavements, the effect is beneficial. In fact, a lot of work has been done in UK and other places, where they are able to clearly show that the use of geotextiles and geogrids considerably reduces rutting. The other important point that we have is that you have to repair the roads, right. That is called overlaying of a pavement. Okay. So, geotextiles can be used as alternatives to stress relieving granular layers, like why do you put granular layers? It is because they take stress, right, because of the load dispersion capacity. So, then in some cases the people put seal coats, rubberized asphalts, all these materials for controlling surface moisture infiltration, retarding reflection cracks in pavement overlays. Okay. So, instead of that, one can use a geotextile. So, in pavement overlays or in the pavement rehabilitation, geotextiles are very useful compared to some of these things, like they help in normally conventional highway engineers or pavement engineers, they know about this use of granular subbase. They say that you provide higher thickness of granular base, or provide a seal coat, or provide rubberized asphalt, which can take care of cracks will not be there, or even for controlling moisture. All that can be avoided by a grid textile. A properly installed and asphalt saturated geotextiles also. So, sometimes you can take a geotextile and immerse in bitumen at a very high temperature. It can work as a moisture barrier. Geomembrane we have, say geomembrane could be expensive. So, what do? Anyhow, you are doing a road work, you have a bitumen. In fact, bitumen is actually geomembrane is also from that processing and coal tar product. But whatever, one can say that if you want to really work, see that the moisture barrier, it acts as a moisture barrier, you can take a geotextile, dip it in the bitumen, and it becomes a moisture barrier, and it helps in prevention of ingress of water. Okay. In some cases where you want to avoid the water movement, you can make it as a moisture barrier, and see that that's quite effective. So, geotextile, it acts as a stress relieving layer. It's a undoubtedly it acts as a stress relieving layer, because it can take some load, and when you install it properly, there is a method of installation, like the way it should be cleaned properly, and there are different types of failure, like a debonding is a quite normal thing, that delamination, because layers, they are all constructed in layers come out, you see in road work the layers come out, and the possibility is that if you are able to use geotextiles, and there are some more products, one can effectively increase the life of the overlay and also the pavement section. That is a very important thing, and they are also cost effective. In fact, I know that we have the Yelahanka airfield pavement, which was being used for aero shows. Even now it is being used, and they wanted to rehab. The thing is that, say, when the flights come and take off, they introduce a lot of stresses into the pavement, like the stresses at the top layer are going to be very high, while landing as well as taking off, the stresses are going to be very high. And what they did was that at the top they put a very high tensile geo grid, which is called glass grid, and it has been very effective. And it is so stiff that it is stiffer than actually a conventional geo grid, and it is very much required there, because they need to develop that much of tensile force, and also must be very stiff. So, like that, the people have been using some of these materials in a very successful manner in most of the pavement construction, particularly when you are trying to handle the soft soils. So, with this I would like to conclude. I would like to say that the pavement design using geosynthetics is a simple approach, which is given by Geraud and Nore, and there are a lot of advances in the recent times. In fact, what was suggested was for geogrids, but that was in 1978 and 1984 and 1990s, even in the latest 2004, you have an excellent papers on geogrids, which can be very useful, and they are quite efficient in helpful. The design methods are very consistent in field applications also, because what is happening is that many of these failure mechanisms of fatigue and rutting are actually you observe them in the field, you do not want them actually. If you have a big rut formed or a lot of cracks in the pavement, maybe our design is perfect, like a CBR design is nice or some other design is correct, but they will not tell you, they will not be able to explain why these failures are occurring. So, that is one design issue, but the best way is to avoid that problems, So, you put some nice appropriate geogrid, and it improves the quality of the design is okay, and the quality of life is also okay, service is also okay. All of this the serviceability performance, the pavement thickness reduction, all things are possible. And in fact, in India, Indian Roads Congress has some specifications, and in many places people have been using in road design extensively, and like a lot of field trials have been conducted, and even in particularly this is one thing in soft soil. See, for example, many people they have done a lot of field experiments where the soil is so soft, you have one soft, so you know the thickness and then you provide as per conventional design, then you come out with some other design using geosynthetic like a geogrids, then you can go for a geotextile, all of this, and they did lot of field tests in the sense in assessing the pavement performance. There are some many equipment which can assess the field performance, particularly in the case of roads, like using falling weight deflectometer, using roughness measurements like profilometers and all that. There are so many equipment in the pavement engineering that one can use and link it to its performance. So with this I will conclude. Thank you.